Well, we'll see. Okay, thanks a lot for the invitation. Because I realized that what I'm going to talk about is a little bit off the main topic of the workshop. So I hope you'll bear with me. So what I'll talk about, which will mainly be neutrino physics. But if you think about observational cosmology, if you think about structure formation, for example, effects on the microwave background radiation, there are some similarities between dark energy, modified gravity, and neutrinos, and therefore I think it's relevant at least to know what the effects of neutrinos are on cosmological observables, such that you can better understand how neutrino physics might influence your attempt to measure, for example, dark energy properties or modified gravity. So just to start us out, this is just the one transparency about neutrino oscillations that I have, basically. So the idea is, of course, that the neutrino states that we know and love are what is called flavor states. So these are either electron, muon, or tau neutrinos. So these are associated with the charge current interaction. Then we have a corresponding set of mass eigenstates. And what we do know about neutrinos is that these two sets of states are not equivalent. They are related by the mixing matrix, which you can, interesting. So a little bit on the left here is missing. But okay, this is U. This is just one way to parameterize the neutrino mixing matrix. The point is, of course, that there are some mixing angles that you need to measure. There are exactly 3 of those. Then there's one CP violating phase. And if neutrinos turn out to be Majorana particles, so if they're their own antiparticles, there will be an additional 2 complex phases that in principle can be measured. Actually, for most of the talk, this will be irrelevant because in cosmology, especially if we think about structure formation, the impact of neutrinos is via their contribution to the energy density, not to the flavor structure, not because of the flavor structure. So actually, the states that we're mainly interested in are just these ones here, and therefore the mixing matrix as such doesn't really matter. Of course, there's a big industry to measure the properties of the neutrino mixing matrix, but it's not really relevant for what we're talking about here, at least not if you just talk about standard model neutrinos. Okay, so if we put it into mass language here, then of course, apart from the mixing angles, you need to have different masses for the different neutrinos, otherwise you don't have oscillation effects. You'll have everything propagating with exactly the same velocity. But since we do have neutrino oscillations, and it's measured in many different places, we know that there are at least 2 mass differences. One historically is associated with what is known as the atmospheric neutrino anomaly that has also been confirmed in long baseline oscillations. The other one historically was always associated with the solar neutrino anomaly that has been confirmed also by the Camland reactor experiment. So we know there are 2 mass differences, which means there are at least 3 neutrino mass eigenstates. So we can put them in here like this in what is known as the normal hierarchy. And what you see here is that there's some arbitrary normalization here, right? So we know that in this case one eigenstate is lighter than the other 2, but we don't know exactly where it is. And the reason is that if you think about neutrino oscillations, we're thinking about differences in velocity, and therefore the absolute mass doesn't really matter, at least not in the ultra-relativistic limit. What matters is only the mass difference, and it's even the square of the mass difference. So we can have these 2, this type of scenario. We could also alternatively have what is known as the inverted hierarchy. And the reason we can have this type of scenario for neutrinos is that, well, we know the sign of this mass difference that comes from solar neutrino oscillations is basically because the solar neutrino anomaly would look very different if you switch this, because then it would require the sun to have positrons instead of electrons, which it doesn't. This one, that's just due to vacuum oscillations, so it cannot tell the sign. It doesn't matter what the sign is, you get the same effect. So this is a possibility. Of course, it's different from what you have in in other branches of the standard model, right? You always normally have the first eigenstate being the lightest and the second one heavier and the third the heaviest. But in principle, we could have a different situation for neutrinos. But the main point here really is that we don't know this normalization. So you can shift the mass scale up or down, and we need to find some way of measuring this. So either you can do direct beta decay studies, for example, look for the mass of the neutrino, or you could hope that neutrinos are Majorana particles, because in that case you have neutrinoless double beta decay going on. Or you can do neutrino cosmology, because that's also sensitive to the neutrino mass via its effect on the energy density. So to a cosmologist, what you're really interested in, like I said, is the contribution to the energy density in the universe. And you can quantify that in terms of the total neutrino mass, because we know, as I'll show you in a minute, we know that what the number density in neutrinos is in the universe, at least we think. And therefore, the only unknown parameter in the energy density is actually the mass of the neutrinos. And not just one of them, but the sum of neutrino masses. Then you can see if you parameterize it in terms of the lightest neutrino mass state, you have these two situations, right? You have the normal hierarchy and you have the inverted hierarchy. And as you increase the mass of the lightest state, starting all the way from 0, then you see the sum goes up, obviously, but also the mass differences go down. And therefore, you eventually end up in what is known as the degenerate regime, where you just have equal mass neutrinos, or almost equal mass neutrinos. That is what can be probed directly in experiments at the moment. But of course, we have reason to believe that our universe might have chosen to be here. So that's the ultimate goal, if you want, of neutrino cosmology, is to measure that neutrino mass, and we'll get there. So just to put numbers into perspective when I start showing them in a minute, let's compare to what you can do in beta decay experiments. So the idea, of course, here is to measure the endpoint out here of the electron energy spectrum, and that is changed if you have a neutrino rest mass. So you can see a change, for example, if you have a 1 eV neutrino here. It's not very easy to see, but it's in principle detectable. At the moment, this provides an upper bound on the neutrino mass. Usually it's called the electron neutrino mass, although of course no such thing actually exists. It's this incoherent sum of neutrino mass states, and it should be less than about 2 electron volts or so. And so if you add those up, you get to a sum of neutrino masses of somewhere around 7 electron volts. So that's the current experimental bound on the neutrino mass. That will be bettered starting next year by the Katrin experiment, this cultural tritium neutrino experiment, which will take us down about an order of magnitude. And you see, probably some of you at least have seen this picture before. This is the Katrin main spectrometer. Actually, the sensitivity to neutrino mass scales as the square root of the diameter of that thing. So the 0.2 eV, that comes from building this as big as you possibly can. And if you wanted to go down by an order of magnitude, you increase the diameter of this thing by a factor of 100. Right? So that's not really feasible. And actually, just a fun thing. So this picture was taken in the streets of Copenhagen in the not too distant past. What you see here are experiments that look a bit like Katrin. These are actually beer fermentation tanks from Carlsberg. So they look almost identical. So probably not on the inside. Okay, so then this was sort of much of the standard model neutrino physics that is relevant to cosmology. But in recent years, there's been a lot of discussion about a possible fourth or even a fifth neutrino mass eigenstate. So of course we know from Leb that there cannot be any additional neutrino flavor states that are charged under weak interaction unless they're heavier than about 45 GeV, and therefore not interesting in this regard. But there might be additional sterile states that are not charged, and associated with those, you might have additional mass states. And that, of course, sounds kind of ugly. The point is that there's a bunch of experiments all pointing to the existence of these additional sterile neutrinos. So I won't bore you with the details, just tell you that there are a number of experiments measuring spurious, if you want, appearance of electron neutrinos from muon neutrino beams, indicating sterile or mainly sterile neutrinos with a mass around 1 electron volt, perhaps a few electron volts, with a relatively small mixing angle if you compare it to the standard model mixing angles. There are also electron neutrino disappearance experiments. These are mainly reactor-based experiments. Then there are muon neutrino disappearance and so on. So the point is, there's some reason to believe that there's an additional fourth neutrino mass state with a mass of around 1 electron volt, maybe a few electron volts. That turns out to have very profound implications for cosmology, as you'll see later, but it's for now just something to bear in mind that there are experiments pointing in that direction, and cosmology might have to live with a sterile neutrino of 1 eV mass. So then, of course, we have to find ways to accommodate it in cosmology if it exists. So what exactly is it that neutrinos do to cosmology? Well, first and foremost, of course, they are a source of energy density. So if we know the number density of neutrinos, and that we think we do, at least for the standard model neutrinos, they're just normal weakly interacting particles, so we know the effective temperature, we can plug that in, calculate the number density, we can translate that into omega, and then we see that if the sum of neutrino masses, if it was about 10 electron volts, then all of the dark matter essentially could be in the form of light neutrinos. Of course, we know that cannot be the case, because neutrinos have these free streaming effects. So essentially they are light particles, they move very fast until they go non-relativistic late in the evolution of the universe. And if you want to see a more graphic representation of this, you can see what happens in standard lambda CDM. This is an n-body simulation of standard lambda CDM. This is one with massive neutrinos, so you replace the dark matter essentially by massive neutrinos. You see the same large-scale structure, but you see no small-scale structure here. So you wouldn't have galaxies or structures less than about a supercluster in such a scenario. So obviously, that is ruled out. Right? So the cosmological neutrino mass bound, whatever it is, must be far superior to the current experimental upper bound, because otherwise you get really, really nasty effects on structure formation, which you cannot allow for. Okay, so to get a real bound, of course, you take all your available cosmological data, you grind the wheels of your Markov chain Monte Carlo or whatever, and out comes some number. Right? So we take the Planck data, the large-scale structure data, which turns out to be very important. So this is one of the latest incarnations of the Sloan Digital Sky Survey. Just let me show you briefly what happens with something like a large-scale structure power spectrum if you have massive neutrinos. So this is the matter power spectrum divided by the power spectrum for standard lambda CDM. So for a neutrino mass of 0 electron volts, you basically just get the standard lambda CDM model, but then you see as you increase the neutrino mass, you get a suppression of power. That comes from this free streaming effect, and actually it's a very, very strong effect because of metric feedback. So not only do neutrinos not cluster, they cause the cold dark matter to not cluster either. So you see, for example, if you have a 1 eV neutrino mass, you suppress structure by 50% on small scales. Even if you had a neutrino mass of 0.05 electron volts, you would have an effect of several percent. So that is about the same order of magnitude that we hope to measure with the Euclid survey, for example. And that is designed primarily, of course, to measure dark energy / modified gravity. So if we would ever hope to measure those things, then we'd better get our calculations of neutrinos correct, because they are going to influence whatever we measure about dark energy, whether we like it or not. Okay, so you take all that data, and then you do your Markov chain Monte Carlo, then you get some number out. This is a figure from the very recent Planck data release. What you see here is the sum of neutrino masses and the Hubble parameter, and it's inversely correlated. So the upper bound on the neutrino mass from the Planck data alone is somewhere around 0.8 electron volts, roughly. A little bit less, but in that ballpark at the 2 sigma level. Then if you add other types of data, of course, you get a more stringent constraint. Right? If you add BAO data, you get a much better constraint. It goes down to about 0.3 electron volts. If you add other types of auxiliary data, you can push it down even further. This is the most stringent bound, I think, published. This is from the, okay, it's from before the last data release of Planck, but that's not going to change things very much, because most of the constraint in this paper actually comes from the combination of Planck data with data measured in what's known as the Lyman alpha forest. So this is measuring the power spectrum on very small scales at very high redshift. And that is very sensitive to the neutrino mass, obviously, because at small scales you saw this major suppression of power on at very high redshift. Structures are, well, close to linear, which means that hopefully you could believe this more than you would a corresponding measurement at low redshift. And, well, then you get a number out. You see here is the neutrino mass, and you see a very tight constraint down here in the end. The problem is that this may not be very robust, simply because we don't know very much about this Lyman alpha forest. In order to get constraints out of it, you need to actually understand fully nonlinear physics in the interstellar medium at very high redshift, and we don't really know if we do that. So instead of quoting a huge list of numbers, because there are hundreds of papers, even from the past few years, quoting numbers in terms of neutrino mass, let me just put it into this 2D plot and say that from the CMB only, of course, you get a not so stringent constraint. On the other hand, we think we know the CMB quite well, and therefore we might actually believe the number that we get out. Then we can start piling data sets on top of each other, and eventually, of course, we get a very stringent constraint. We might even get a detection. But the problem is that we might not believe it, because it might not be very robust. After all, if you keep adding data sets with unknown systematics, then of course at some point you are more likely to see systematic effects than real physics. You would also start from the simplest lambda CDM model, but then you might think that may be too conservative. There could be tons of other physics going on. You could have modified gravity. Modified gravity is known to change neutrino mass bounds. You could also play around with various types of dark energy and so on. And of course then you can never really constrain neutrino mass. And that actually relates to the problem I talked about before. The effect of neutrino masses is very similar to many types of dark energy and modified gravity in terms of this type of observable. And therefore, if you cannot disentangle them, you never know if you're actually measuring massive neutrinos or you're measuring something, in a sense, more interesting, namely modified gravity. So that is something that has to be figured out. We have to understand exactly how are they distinguishable, or are they even distinguishable. So that is just a list of how one can possibly avoid these neutrino mass bounds. I will talk more about especially this one in a minute, because that's very interesting in relation to these sterile neutrinos. Just let me show you one example. This is an old example by now, but it still holds true to some extent. Namely that if you just have standard dark energy, okay, this is now, think about it as something that acts only on the background, not at the level of perturbations, only on the background. So it causes expansion to be different. Then you can see that the neutrino mass is actually extremely highly correlated with this parameter. And therefore, it's very hard to know if you're measuring, for example, a massive neutrino in a phantom energy model, or you're just measuring standard lambda CDM. So this is just a warning that these things are, in fact, very, very correlated. Okay, so in neutrino physics, we can also go beyond just the mass and look at, for example, this number density of neutrinos. And I said before, of course, that in the standard model, we can calculate this parameter extremely precisely at the sub 1% level of precision. That will give us exactly the number density that we need to calculate omega. But we might also take this to be a free parameter in a sense. After all, there might be non-standard physics going on. There could be additional degrees of freedom that may or may not be thermalized in the early universe. Or neutrinos might not behave the way we think they behave. They might have chemical potentials. They might be produced by heavy particle decay and whatnot. So really we should think about this as yet another parameter to be measured experimentally. So this is what some people call dark radiation, and the Planck people and many others have tried to measure this number. So this N effective, that is the so-called effective number of neutrino species. The standard model prediction is that it's 3.046 roughly, and this is not because there are 3.046 neutrinos, obviously, it's just a way to parameterize energy density. So that corresponds to the energy density that you have in the standard model. And you see the Planck measurement is exactly compatible with that number. So there seems to be no evidence, at least, for non-standard things going on. But I should remind you, and that actually becomes quite important, and certainly also important in models of dark energy and modified gravity, that in extended models, such a conclusion cannot be expected to hold. So as soon as you have a more complex model parameter space, you can easily have models that prefer extra energy density. And I'll show you an example of that in just a minute. So this is just a word of warning that this seeming evidence for the standard model, or rather evidence against any non-standard physics, that only holds because it's a constrained model we're looking at. And of course, this now brings us back to the question of the sterile neutrino, because after all, I just told you that there is this tentative evidence, at least, for a massive extra neutrino mass state. And that, for sure, if it's thermalized in the early universe, will have a profound impact, right? It's an extra neutrino species. So that would give us about 4 degrees of freedom, or 4 neutrino degrees of freedom. So we would be somewhere out here, and that is seemingly highly excluded by cosmology. So then we need to figure out some way of reconciling the two if it actually turns out to be there. Of course, many people have looked at the impact of such sterile neutrinos on structure formation. Let me show you just the most recent one. That is, again, from the Planck publication from last month. So this is the effective mass of the sterile neutrino. It's just a slightly different way of parameterizing the mass. And the total ineffective, which again in the standard model is 3, so standard lambda CDM is in here. But you see that there are plenty of models that would indicate that a mass maybe up to 1 eV or so is okay. But if you combine a mass of 1 eV with something that is completely thermalized, then you are up here, and that is clearly not favored by cosmology. Yes?
But this effective neutrino species is at the time of Big Bang nucleosynthesis or today?
This is actually at the time of CMD formation, so it's right in between.
Yeah.
So the energy density could have been produced after BBM, that's entirely possible.
Ah, it's possible, okay.
But we would not be able to measure this number today at this level of precision, simply because there are no observables that are really sensitive to the relativistic energy density. Okay, so then you can play the game of overlaying. The blue curves are essentially the same as I showed you on the previous transparency. You can overlay those with the short baseline neutrino oscillation data, and you see they are actually pretty much compatible. But what you should actually look at here is the fact that if you have a mass of 1 eV, it's very difficult to have it completely thermalized. So these plots were made before the last incarnation of the Planck data, and they would look worse now because the blue contours would be much smaller and leave much less room for something up here, which is actually where we would expect the extra sterile neutrino to be. So the bottom line that you should take away is that, well, the sterile neutrino cannot be accommodated within cosmology if it's fully thermalized and if it behaves like a normal neutrino, meaning that it free streams and so on. So we have to find ways around this. So either we should prevent the sterile neutrino from thermalizing, or we should do something else to it. And I don't want to bore you with the details of neutrino thermalization in the early universe. So let me just very briefly sketch how something like this goes. So the idea is that you have the mass states and you have the flavor states. Right? So the fourth flavor state is exactly sterile. meaning it has no interaction whatsoever. But because it mixes, it means that the fourth mass state actually has a small flavor component. So every time you have a neutrino scattering, there's always a finite probability that it ends up in the sterile state, right? And the amount of neutrinos ending up in the sterile state depend on the scattering rate and on the effective mixing angle. So the higher the mixing angle, the more sterile neutrinos you produce, the higher the interaction rate, well, same thing, because you have more of these events that can lead to the production of sterile neutrinos. So this is well known, it has been calculated in literature many, many, many times. You can solve a Boltzmann-like equation. It's usually called the quantum kinetic equation at this level. So it's like the usual Boltzmann equation. It just follows the density matrix instead of the one particle distribution function. And if you don't take scattering into account, then you can describe neutrino oscillations in this way. It's just like spin precession in a magnetic field, basically. Then you can add interactions. The first order interaction that you get is just a change in the background potential. This is what is known as the MSW effect. So you change the effective mass of a neutrino because it interacts with the background, and that occurs, of course, only for the active neutrinos, not for the sterile one. So you add a term in on your right-hand side to the effective potential. Then at second order, you have all kinds of things going on. Like I told you before, of course, you have scattering, so that needs to be taken into account. You also have what is known as the quantum Zeno effects. Like if neutrinos are oscillating and you kick them, then you reset essentially the oscillation. So it's like a measuring process. Every time it interacts, you measure it, and therefore it becomes difficult for it to oscillate. And you have, of course, the usual production and annihilation of neutrinos from the thermal background. That's like the usual term in the Boltzmann equation if you think about dark matter production and annihilation. Same thing here. This is what the equations look like. I won't bore you with the details, but just show you the result. So this is the effective number of degrees of freedom that you end up with. So this is ineffective, basically, for sterile neutrinos. So you see, as you increase the mixing angle and you increase the mass difference, you produce more of these neutrinos. And up here, which is where the short baseline anomaly says that neutrinos, the sterile neutrinos should be, you have complete thermalization. So there's no way of avoiding thermalizing this sterile neutrino. This is true in the normal hierarchy and it's true in the inverted hierarchy. Right? So we need to do something. One thing that has been tested and known to work is to add a lepton asymmetry. And the reason that works is basically because if you add a lepton asymmetry, you shift the temperature where sterile neutrinos are produced downwards. So essentially you keep sterile neutrino production from happening until a much later time where neutrino interactions are much slower, and therefore it's very difficult to produce extra energy density. That's why it works. So this is a known loophole, so to speak. But neutrino chemical potential, on the other hand, is not a very nice thing, it's not a very natural thing, because why would it be in the neutrino sector but not everywhere else? We know other chemical potentials are very small, so why would you have a large chemical potential in neutrinos? And furthermore, one that you would have to produce way below the electroweak phase transition. So it would involve some not so straightforward physics, presumably. Okay, so one thing we looked at, and other people also started looking at, was whether additional interactions can also do something like this. Could you imagine that the sterile neutrino world actually has a new interaction that it's charged under? Maybe an interaction that also applies to dark matter, for example. This is something that many people have been looking at. And the answer is that yes, that actually can have an effect. So we added just, again, I won't bore you with the details, just the only thing to bear in mind is that if you charge the sterile neutrino under a new Fermi-like interaction with fundamental coupling and an effective mass of the mediator particle, then you can actually strongly suppress the formation of these sterile neutrinos. You see, the stronger you make the interaction, the more you suppress the formation of sterile neutrinos. And again, the reason is pretty much the same as before. It's because you have a matter potential that delays the production of sterile neutrinos until the point where you cannot thermalize neutrinos anymore because they're decoupled. So that works. One thing, though, that was pointed out relatively recently is that, well, yes, even though these sterile neutrinos are not produced at high temperature, they would still be produced at low temperature by conversion of normal neutrinos. So even though it doesn't produce extra energy density, it shifts the ratio of energy densities, right? So it takes only standard model neutrinos and transfers some of it into the sterile neutrino, which has a mass, and therefore this type of model will still be subject to, well, the standard cosmological neutrino mass part. Okay, so what could be done about this? One thing that could be done is to go away from the Fermi-like interaction, charge the sterile sector under a new pseudoscalar interaction with a massless mediator. So this is something, for example, that one would typically have in what is known as Majorana models. This is a particular type of mass generation model for neutrinos. But the point is that that also induces a new matter potential for sterile neutrinos and leads to suppression of formation of sterile neutrinos. But it has another effect which is actually even more interesting. That is that if this mediator particle is massless, these sterile neutrinos actually interact stronger and stronger and stronger and stronger while the temperature is going down. So these neutrinos actually start out of equilibrium and then they come into thermal equilibrium. And at the present they would be extremely strongly interacting. So you have this whole new sector of very strongly interacting particles. You can think about it as a fluid. And one thing that it does is that it suppresses what is known as anisotropic stress. It's just another way of saying that in this type of model, there's no neutrino free streaming. If all neutrinos behaved like that, that would be very, very strongly excluded. This is something that has been known for a decade. But if you only have the sterile sector charged under this new interaction, then actually it turns out that this provides a much better fit to data than standard lambda CDM. Okay, much is maybe stretching it, but it has a delta chi-square of about 10 or so, which is sort of significant. So actually you can have very, very, very good fits to all known cosmological data, and it would be a way around the cosmological neutrino mass bound. So that's kind of interesting to think. Other people have played around with charging dark matter under this new interaction, because then you have self-interacting dark matter that also has interesting properties that are perhaps worth investigating more. Okay, so then I have a few minutes left, and I wanted to spend that on, well, something completely different, and something that is perhaps even more relevant to dark energy. And that is how we can understand the differences between the effect of dark energy and neutrinos on structure formation on structure formation. So we know that, for example, Euclid, this is true also for the LSST, will give us extremely precise data when it comes to the power spectrum, measured from weak lensing, measured from a spectroscopic survey or photometric survey. And if you just look at the ability, for example, of it to measure a neutrino mass, this is a calculation that we did a few years ago, and it shows you that the Euclid data in combination with data from Planck will actually be able to, at somewhere around 5 sigma, measure the neutrino mass, even in the most pessimistic case when neutrino masses are completely hierarchical, so that the sum of neutrino masses is 0.06 electron volts. That's very impressive. And actually, this conclusion holds even in the case where you add, well, not arbitrary dark energy, of course, but at least you add time-varying dark energy, for example. You can actually measure both the dark energy parameters and neutrino masses very, very precisely by combining different types of observables. Now, that looks very nice, and of course many people are quite happy with the prospects for experiments like Euclid. But one of the problems that's hidden in something like this is that it assumes that we understand all systematic issues in the data at the required level of precision. So for example, if we look at something like the weak lensing power spectrum as measured by Euclid, this is approximately the type of error bar that you would expect on CL, so on the lensing CL power spectrum. You see that it goes down to something like 1% at high L, and this is where most of the constraining power is, of course. So it also means that you need to understand all systematics at the same level of precision. And this is particularly nasty if we talk about lensing, because after all, this is something that lives on a sphere, like the CMB, which means that you take out the third dimension by integrating along the line of sight. But that also means that you have contamination of power from very, very small scale. So essentially high K modes will contaminate even the signal at relatively modest L, meaning that you wouldn't in principle think you would be looking at small to medium-sized K. So that's just this integration effect. So that means that if we're ever going to extract useful information from weak lensing here, then we should understand the power spectrum also for high K. That, of course, is very difficult. The main difficulty might even just be in the baryonic physics, but that's too difficult, so we're not working on that. We leave that to other people. But there's other interesting stuff to do, for example, related to neutrinos, stuff to do with modified gravity and dark energy that should also be there at the level of n-body simulations. I can show you one example of what happens if you add neutrinos, and then I'll show you in a second what happens with the dark energy. So what happens with neutrinos is you get the same type of curve that I showed you from linear theory. That's the green type of curve. You do get this power spectrum suppression. But then you see there's an additional suppression here indicated by the colored curve. So that's a fully nonlinear effect that needs to be in there. And it's not a negligible effect. It's something that has to be there if we're going to extract useful information from the data. Then you might wonder, is this a particular effect of neutrinos, this suppression dip? And it turns out it's not. It's actually something that is a transient, it's well, a signature of a transient effect in structure formation that I'll show you in a minute, that would also be there in models of dark energy that suppress structure. So you see the effect of a massive neutrino here, and here you see what happens in a model with dark energy with an equation of state different from -1. It's just taken to be -0.6, it doesn't matter. This is just to give you an example of a model with suppressed structure formation. So the black line here is the linear theory, and then you see the n-body result gives you this very, very pronounced dip, and then it goes up and it actually goes above the linear theory result. Same thing for the neutrinos, even though, of course, the linear theory background is slightly different. So how does one explain an effect like this? Well, it actually turns out to be an effect of the way structure forms. So you see here, as a function of wave number k, you see the linear power spectrum here, and the corresponding nonlinear power spectrum here. You can also, this is measured in wave number, but you can also think of this as something that's actually measured in time, where a small scale mode has had more time to grow during the evolution of the universe because it came inside the particle horizon much earlier, and therefore had more time to grow. And a large scale mode, of course, is the opposite. So you see here on very large scales where there's very little growth of structure, everything is just linear. Then there's a period where structure grows extremely fast, and then it settles back into a new rate of growth, which is known as the stable clustering limit. But initially you just have collapse of structures. That's a very rapid process, and that's why you have this extra fast growth here at the moment. And then actually, if you compare two models, you see this effect very pronounced, right? So initially you see one model, namely the standard lambda CDM model, going non-linear, structure forming very fast. That means that the ratio goes down here because the dark energy model, or the neutrino model, lags behind. And then at some point it slows down again and reaches the stable clustering limit. So this now goes up again because now the standard lambda CDM model slows down while the other one is still catching up. And then it goes back up here. And actually you can show that For a dark energy model, this even goes back to 0 here, funnily enough. So on small scales, there's no difference really between a modified dark energy equation of state model and standard lambda CDM. So this is the type of thing that we might want to look for and understand the differences here when it comes to dark energy versus modified gravity versus finite neutrino mass. And of course, we need to put all of these effects into our simulations. At the same time, it's not enough to simulate one effect at a time. We need to do all of them simultaneously. So that's something that we're working on, and of course something that one should be working on, because we know that we will have experiments like Euclid and LSST in the not so distant future. Okay, so conclusions. Well, again, I know this was somewhat off topic of the main thrust of the workshop, but I hope I convinced you that at least there's interesting information to be gained about neutrinos from cosmological observations. I hope I convinced you that the sterile neutrino thing is actually worth looking into, because there is quite a lot of experimental indication that something like that might be there, and it's worth investigating what it does to observational cosmology. I hope I also convinced you that in the very near future there will be all kinds of interesting data to look at with regards to dark energy and neutrinos. And I hope really I also convinced you that we are very, very far from a complete understanding at the level of real numerical simulations of structure formation. So there's lots of work to be done, and I think my time is up, so I'll stop now.